Hello, this is Alex with Live at Phuket PALS. Welcome to another GED science class. Today we will learn about chemical reactions, chemical formulas, and equations. So first of all, a little overview. We will learn and discuss what a chemical formula is, what chemical reactions are, what chemical equations are. We will learn about the law of conservation of matter, or the law of conservation of mass, how to balance chemical equations, what a limiting reactant is and what a reactant in excess is, and we will learn about different types of chemical reactions. Okay, first of all, what is a chemical formula? A chemical formula of a compound, like CO2, shows how many of each type of atom join together to make the compound. For example, in iron sulfide, every iron atom joins to one sulfur atom. So we show its formula as FeS. In sodium oxide, there are two sodium atoms for every oxygen atom. So we show its formula as Na2O. Notice that the 2 is written as a subscript, a small number. So written in this way, Na2O with a big 2 would be wrong. The chemical formula, if we have more than one atom of a type, we write it with a small subscript. Down here we see a diagram that shows one carbon atom and two oxygen atom combined to make the unit of carbon dioxide. The chemical formula is CO2. Sometimes we see more complex formulas such as FeOH3. A unit of FeOH3, which is iron hydroxide, contains one iron atom, 3 oxygen atoms, and 3 hydrogen atoms. We write it in brackets, and the brackets, whatever the brackets include, their subscript applies to that. So the 3 and the subscript applies to the O and the H. Chemical reactions. A chemical reaction is a process that leads to the chemical transformation of one set of chemical substances, the reactants, to another, the products. The substance or substances initially involved in the chemical reaction are, as we already said, the reactants or reagents. Chemical reactions are usually characterized by a chemical change, and they result in the formation of one or more products, which usually have different properties from the reactants. Burning fuel, smelting iron, making glass or pottery, or brewing beer, or making wine and cheese are among many examples of activities incorporating chemical reactions that have been known and used for thousands of years to humans and by humans. The basic chemical equation is set up in the following way. We write the reactants on the left side, and then we write an arrow and the products on the right side. The arrow reads or means reacts to form. So for example, hydrogen plus oxygen react to form water. So the example above here is a word equation. In a word equation, we simply write out the names of the reactants and products. For chemists, a more convenient and common way to formulate the reaction is expressed in a symbol equation. A symbol equation allows chemists to work out the masses, concentrations, or volumes that will be needed to react and produce a certain amount that is wanted by the chemist. There we use the chemical formulas in the equation, which we have just discussed before. So the same equation, hydrogen plus oxygen reacts to form water, is written below here in a symbol equation. So we have 2H2 plus O2 gives 2H2O. We already discussed the subscripts, the small numbers. tells you how many atoms of a particular element are in the compound. So H2O has 2 hydrogen atoms bonded to 1 oxygen atom. The big number in front, the coefficient, tells you about the total number of molecules of that compound used in the chemical reaction. The chemical reaction always shows the smallest ratio of molecules reacting with each other. We can see as well the small letters in brackets. These are sometimes used, but not always. And they tell us about the state of matter that the substance is in. We have 4 so-called state symbols. We have the S in brackets, which means the substance is in the solid state. We have L for liquid state, G for gaseous state, and AQ, which means aqueous, and that stands for, or relates to a substance that is dissolved in water. Okay, why do we need the coefficient in front in a chemical equation? That relates to the law of conservation of mass. The law of conservation of mass, or matter, states that matter can neither be created nor destroyed in a chemical reaction. For example, processes that change the physical or chemical properties of substances within an isolated system, such as conversion of liquid to gas, leave the total mass unchanged. Same in a chemical reaction. The mass of all the reactants is equal to the mass of all products being produced. Down here we have an example. We can see a closed system and 2 chemical substances, calcium chloride and sodium sulfate. They react with each other. Calcium sulfate forms in a sodium chloride solution, and we can see that before and after the reaction the mass is unchanged. Now you might ask yourself, well, that applies here when 2 liquids react to form a solid and a liquid, but what about a situation where wood is burned? When we have a campfire, well, we start with a lot of wood, and after we burn it, which is a chemical reaction, there's only some ashes left. And the amount of ash is definitely not the same mass as the wood that we have started with. So does the law of conservation of mass apply here? Well, it does, because the product of the reaction when wood is burning is not only the ash that is left over, but the main products of this reaction are carbon dioxide, which is a gas, and water vapor, which is water in the gaseous state. And both these gases will escape. So in case of the fire, we do not have a closed system. This is why there's less mass in the end than before. If we would burn everything in a closed system, we would catch all the carbon dioxide produced, catch all the water vapor produced. The mass before and after would be the same. So how do we balance chemical equations? Since matter can neither be created nor destroyed, we need the same amount of atoms of each element on the reactant and the product side of the reaction. The process of achieving this is called balancing a chemical equation. When balancing an equation, we change the coefficients only. Now you remember the coefficients are the big numbers in front. We do not change the subscripts. We do not change the small numbers, since the compounds have fixed ratios of the atoms. Now the chemical formulas have to remain the same. They are defined. Aluminium oxide is always going to be Al2O3. So we can only change the big numbers in front. As we can see, when we just write down aluminium plus oxygen gives aluminium oxide without any coefficient, this reaction up here is unbalanced. On the left side we have 1 aluminium, on the right side we have 2 aluminiums. On the left side we have 2 oxygen atoms in a molecule O2, on the right side we have 3. so the reaction is not balanced at the moment. The law of conservation of mass does not apply. So we need to balance it. The balanced chemical equation is we need 4 aluminiums to react with 3 O2 molecules to give 2 aluminium oxides. We need to make it a 2 here because otherwise we couldn't have 3 complete. We wouldn't be able to balance the oxygen. So how to get to this final balanced form? We will discuss now the steps to achieve this. The steps to balancing a chemical equation. So first write down the unbalanced chemical equation. Then identify each element found in the equation and list the elements under the equation on both sides and count the number of atoms present on each side in the unbalanced equation. Start balancing by changing the coefficients, the numbers in front of the compounds or molecules, so that the number of each atom of each element is the same on both sides of the equation. A good rule of thumb is to start balancing the largest compound first, working your way down to the small compounds or elements. If O2 is present, usually balance it last. If there are charges present in the equation, these need to be balanced too. We will not have a look at this in this class. And last step, practice makes perfect. So you should practice this quite a bit until you feel comfortable balancing the equations. Okay, let's go over an example, the same as we had before. Write down the unbalanced equation. Aluminium plus oxygen gives aluminium oxide. Here we have the unbalanced equation. Al plus O2 gives Al2O3. Now let's list the elements on both sides and count the atoms present. So we list Al and O on both sides. At the moment we have 1 aluminium and 2 oxygen on the left, 2 aluminium and 3 oxygen on the right. Now let's start balancing the atoms step by step. We could start with aluminium here. So since we have 1 on the left and 2 on the right, we change the coefficient on the left side in front of aluminium to a 2, and we change the counting below to 2 aluminium atoms. So at the moment aluminium is balanced. Now oxygen is a bit more complicated. We have 2 on the left, 3 on the right. On the left side we have O2. So we cannot make it 3 because we can only add whole molecules. Our coefficients can only be whole numbers, not decimals or fractions. So the next whole number that we could get to with O2 is 4 oxygen atoms. 2O2, 4 oxygen atoms, not 3. So instead we have to make on the right side the oxygen an even number. The only way of doing that is changing the coefficient in front of aluminium oxide to 2. That will give us 6 oxygen atoms on the right. And don't forget about the aluminium now. If you add a coefficient in front of aluminium oxide, we have now 4 aluminium atoms. 2 times 2 and 2 times 3. That means to get 6 oxygen atoms on the left side, we need to have 3 oxygen molecules. 3O2, 3 times 2 is 6. Now the oxygen is balanced. We have to be careful. We started balancing aluminium, but we have changed the aluminium on the right side again. So we need to go back to aluminium and change the coefficient again to a 4. Now we have 4 aluminiums on the left, 4 aluminiums on the right, 6 oxygens on the left and 6 oxygens on the right. The equation is balanced. Okay, here are some examples of unbalanced chemical equations. And if you want to practice, you should stop the video now and write down these equations into your notebook and try balancing them. If you're not sure how to do it, you can rewind the video a few minutes and look at the steps and the example of balancing the previous equation again, and then try your best to complete these 8 examples. So please pause the video now, because now I will continue. At the end of the video, you will see the solutions. So, as we already learned, the law of conservation of matter states that matter can neither be created nor destroyed in a chemical reaction. It leaves the total mass within a system unchanged. So let's have a look how this exactly applies to the mass in this example. We have methane, which is CH4, that reacts with oxygen, O2, to form carbon dioxide and water. So let's say we have 16 grams of methane, and they react with 32 grams times 2, so 64 grams of oxygen, and we will get 44 grams of carbon dioxide. So since we have a total of 80 grams of reactants, what do you think is the total in grams that we receive on the product side? If we apply the law of conservation of mass, you're correct, we will as well yield 80 grams. Since we know that we receive 44 grams of carbon dioxide, I'm sure you can figure out how much water we will yield in this equation. We will get 36 grams, or 2 times 18 grams of H2O. So, what are limiting reactants and what are reactants in excess? In the laboratory, if we go back to the previous example, very often we don't match exactly the masses of the reactants. Very often we have of one of the reactants a lot more than we actually need. And that means that of the other reactant we have less than we need to react all of the reactant of which we have too much. So the limiting reactant is the reactant in a chemical reaction that limits the amount of product that can be formed. The reaction will stop when all of the limiting reactant is consumed, whereas the reactant in excess is the reactant in a chemical reaction that remains when a reaction stops, when the limiting reactant is completely consumed. So we have the same example again. This time we work with 16 grams of methane and 100 grams of oxygen. We will again get 44 grams of carbon dioxide and 36 grams of water. Now on the left side at the moment we have 116 grams, but we only get 80 grams on the right side. So something's off here. In this case we have one limiting reactant, which is methane, and a reactant in excess, which is oxygen. So not all of the oxygen on the left side, not all of the 100 grams actually react. So only 80 grams in total react, and we will be left with 36 grams of oxygen. In this example, methane, CH4, is the limiting reactant. Once all 16 grams of methane have reacted, the reaction stops, and 36 grams of oxygen will be left over, with oxygen as the reactant in excess. To finish this class, let's have a look at different types of chemical reactions. The first type of chemical reaction is a synthesis reaction, or so-called build-up reaction, where two substances combine to form a single new substance. We can use a general formula here, where A and B represent different substances. A plus B react to form the substance AB. One sort of combination reaction that occurs frequently, or synthesis reaction, is the reaction of an element with oxygen to form an oxide. Metals and nonmetals both react readily with oxygen under most conditions. Magnesium, for example, reacts rapidly and dramatically when ignited, combining with oxygen from the air to produce a fine powder of magnesium oxide. The example equation we see below: two magnesiums react with an oxygen molecule to form 2MgO. you can see this reaction is already balanced. We have 2 magnesium atoms on the left, 2 oxygen atoms in an oxygen molecule, O2, on the left as well. We have 2 magnesium atoms on the left and 2 oxygen atoms on the right as well. The second type of reaction is the opposite, which is called a decomposition reaction. Instead of something building up, this is a reaction where one compound breaks down into 2 or more simpler substances. The general formula is the compound AB breaks down into A plus B. Most decomposition reactions require an input of energy in the form of heat or light or electricity to happen. Metal carbonate decomposes into a metal oxide and carbon dioxide gas, for example. For example, calcium carbonate undergoes thermal decomposition into calcium oxide and carbon dioxide. So we need to apply heat, we need to put some energy in so that this reaction happens. We can see it below. Calcium carbonate, CaCO3, reacts to form CaO plus CO2, calcium oxide plus carbon dioxide. Another example are metal hydroxides that decompose on heating to yield metal oxides and water. Sodium hydroxide decomposes to produce sodium oxide and water in the equation below. 2 NaOH react to form Na2O plus H2O. Again, all equations in these examples are balanced. If you want, you can pause the video and check and count the numbers of atoms on each side of the equation. Third type of chemical reaction are so-called single displacement reactions or single replacement reactions. A reaction in which one element replaces a similar element in a compound. A plus BC react to form B plus AC. As you can see, A has swapped the position with B. In this general equation, element A is a metal and replaces element B, also a metal in the compound. When the element that is doing the replacing is a nonmetal, it must replace another nonmetal in a compound. Magnesium is a more reactive metal than copper. When a strip of magnesium metal is placed in an aqueous solution of copper 2 nitrate, it replaces the copper in the nitrate compound. The products of the reaction are aqueous magnesium nitrate and solid copper metal. As we can see, magnesium plus copper nitrate, Mg plus CONO32, react to form MgNO32 plus Cu. The last type of chemical equation, chemical reaction, is the double displacement reaction, a reaction in which the positive and negative ions of 2 ionic compounds exchange places to form 2 new compounds. AB plus CD give Ca plus Bc. In this reaction, A and C are positive ions, while B and D are negative ions. Double replacement reactions generally occur between substances in aqueous solutions. In order for a reaction to occur, one of the products is usually a solid precipitate, a gas or a molecular compound such as water. A precipitate forms in a double replacement reaction when an insoluble ionic compound forms. When aqueous solutions of potassium iodide and lead 2 nitrate are mixed, the following reaction occurs. 2 potassium iodides react with lead nitrate to form potassium nitrate and lead iodide. So if you have paused the video and tried to solve the balancing questions, here you have the solutions. I hope you were successful in solving them. If you are able to do these, then you are on the right way to success when it comes to balancing. That's it from me, from Alex, here at Live Phuket PALS. I hope you learned something in the class today, and I hope to see you next time for another science screencast.